Now the next thing I want to do is I want to go over the equations that we were using in Chapter 3 and review how each one is determined, as well as the units used for each type of equation. So the first one that we looked at in Chapter 3 was for speed. Okay? Speed is equal to distance divided by time. So we'll say that d is equal to distance, and we'll continue to use these variables. T is equal to time. Now we talked about average speed being the total distance and then divided by the total time, or instantaneous speed at any given instant in time. We can look down, like I said, in the classic example of a speedometer and know how fast we're going. Now, also said to you that at times velocity and speed are interchangeable, but in fact in physics they are different. Velocity is used with this v, is called out as the variable, and its equation is the same as speed, distance over time. The one difference that we have between speed and velocity is that speed is a scalar quantity, meaning that we only need magnitude to fully define it. So we only need to know a value of speed, and we know what its speed is. Velocity, on the other hand, is a vector quantity. We need both magnitude and direction to fully define it. So scalar quantity is magnitude only is needed. Okay, and vector quantity is magnitude and direction. So velocity adds to it its direction. So if I know what my speed is, but I also know in which direction it is, it becomes officially a vector, or I'm sorry, it becomes a velocity. Now, we can have an average velocity as well, and we note average velocity with a line above it, and that would be the total distance over the total time as well. Okay, so I'm going to put up here v is equal to velocity. Okay. Now the next concept that we had was acceleration. Okay, acceleration is it's going to be equal to the change in velocity over the amount of time it took to get there. So when we say, oh, we went from 0 to 60 in 10 seconds, our 0 to 60 is our change in velocity. We can expand that out by saying we want our final velocity minus our initial velocity divided by the time that it took to get there. Now, often you're going to read problems that'll say starting from rest, we increase our speed to blah, blah, blah over a certain amount of seconds. When we start from rest, or we're told that we're just dropping something, that means that our velocity goes to 0 for that initial, and our final velocity will be what we divide our time by. So just be aware of that verbiage that we see in problems, and we'll bring that up as we come across it. Okay, so VF is going to be velocity final, and VI is going to be velocity initial, and then A is going to be acceleration. Okay. Now the other thing that we can do with this is we can rearrange this to solve for velocity knowing an acceleration that we're under. So we can rearrange this, and so we'll see the equation a lot. V is equal to A times T. Like, what is my velocity at any given point in time when I know my constant acceleration? Now, acceleration can also be denoted as gravity. And for our problems, like I said, we're going to be using 10 meters per second squared in the problems we work in this class, unless otherwise noted. For precision, though, always substitute that value in other places outside of this class for 9.8. Okay. So if we want to know a velocity of a free-falling object, then our v is going to be equal to g times t. So you'll see that the acceleration is going to be substituted by g. Now, let's say we want to know how far something falls, what its distance is. Okay, distance of a free fall, okay, that's when only gravity is acting on it, is going to be equal to 1/2 times the acceleration of gravity times time squared. Okay? And so another equation, just rearranging this, is we can rearrange to solve for our time. We can say t is equal to the square root of 2d, taking the 2 and multiplying it up, divided by the acceleration of gravity. Okay? This can also be substituted back. If we want to know a straight line distance for a constant acceleration, we would say d is equal to 1/2 at squared. Okay, and then the same thing for t here is going to be equal to the square root of 2d divided by that acceleration that we know. Now, not only knowing the equations is important, but also understanding the units associated with each one is very important. So the units for speed, starting at the top here, are going to be distance units, which we're going to say are meters, over time seconds. So meters per second is a common rate or units for speed. We also know that speed on our speedometers, we see it as miles per hour distance over a time as well. That's also valid units for speed. Velocity, same thing. We're going to have meters per second here, okay? Both cases, so this is going to be a meters per second. Acceleration. Acceleration, we have meters per second on the top divided by seconds, which we then say is meters per second squared. And that would be the same thing for gravity as well. Now, when we rearrange things, we always want to put our units in and make sure that the units are coming out correctly. So when we look here at this velocity is equal to g times t, we know g is meters per second squared times a value of time, which is going to be seconds. My seconds on the top here will cancel out 1 on the bottom, and so I end up with meters per second, which are the valid units for velocity. Okay? Now for distance down here in the equation that we have, we would expect that we would end up with distance value. So down here, I'm going to put in d is equal to, our units are going to be 1/2, the g is meters per second squared, times a time squared, which is going to be seconds squared, multiplied on top here. So notice the second squareds cancel out the second squared, and we're left with meters, which is exactly what we need. So it's important when we're writing out our equations and solving for things to add the units in, because that way, if we end up with the correct units in the end, we know that we set up the problem correctly. So understanding that speed and velocity have units of meters per second, that distance has units of meters, that time has units of seconds, that acceleration or gravity have units of meters per second squared, comes in really handy so that we can always analyze if we end up with the right units canceling out, that we set up our problem appropriately. Now, for your quiz, you'll be able to have an equation sheet front and back. So utilizing and reviewing these equations and maybe putting them on that sheet of paper for your quiz will give you an advantage as you take your quiz and do your problems for Unit 2.